strictly speaking, none of this stuff will be examined. So you're probably, okay to take a seat back or to just not take it as seriously as maybe you've taken some of the other material, okay? So here's our goal. Here's what we're going to be working on. So we've been looking at series of functions, but now there's a very specific type of function that we want to look at. And basically, it's like these infinite polynomial things. Okay, so our goal now is we want to look at a series of this form. Okay, so the sum, obviously, kind of like, what you start with doesn't really matter, but I'm going to start at 0 here. Like this. Okay, so CK is just some sequence of coefficients. So those are real numbers. Okay, so CK is a sequence of real numbers. And A is just some real number. Yeah, exactly, power series. Okay, so we call this sort of thing a power series. Often we'll call this thing a power series centered at A. Okay, so this is called maybe let's give that a different color now. Because I could have put this in a definition box, but who cares? So we call this a power series. This is called a power series centered at A. Okay, and there's lots of reasons that you might want to do this shift. A lot of our proofs will, let A be equal to 0, just because it'll make the proofs easier to write down. But I'll explain. I'll show it to you when we get to on how y setting A equals 0 doesn't make a difference at all. And if you go and you do a lot more mathematics in your life, you're going to see these things a lot. So analytically, if you're doing a class like this, what we're really going to be worried about is for what values of x does this thing converge, right? Or what is this thing as a function, right? Because if you think of this as, each of these things as a function, ck x minus, or c2 x minus a squared, that's a function. C3 x minus a cubed, right? That's a function. C4 x minus a fourth, that's a function. So just like we were sort of talking about on Thursday, we can look at this thing as an infinite series and we can say, does it converge pointwise? Does it converge uniformly? What does it converge to? What sort of function does it converge to? Does it converge everywhere? Or does it only converge in some places, right? Those are things we're going to look at. If you go and you take, 202 or 344, actually, I don't think 202 does it a bit, but you'll learn really cool ways of counting with using these things. So you're not worried about convergence at all. In that case, x is just sort of a placeholder. Okay, the exponential of x just tells you some sort of information, but you're not worried about actually plugging numbers into x. So it's a sort of interesting thing, right? That's called combinatorial enumeration. I definitely, even though I'm not like a discrete combinatorist, I definitely thought that was a super cool aspect of combinatorics. So if you ever get an opportunity to learn it, it's very cool. You'll see these things come up in moment generating functions. If you take any statistics, anything like that, they show up formally in algebra. They're just certain things you can do. There's a ring of formal power series. And again, in that case, they're formal. And by formal, again, what formal means here is you're not worried about whether these things actually make sense, right? You're not worried about whether or not they converge. You're just formally writing down this infinite polynomial looking thing. Okay, so that's what formal means. But we are not working with formal power series. We are working with, we want to know when these things converge, right? That's really important for us. So that means we got to prove a bunch of things. Now, we've seen an example of a power series before, and we might just not know it. So for example, we have this power series, right? This is a pretty easy one. It's probably the nicest one we could have. So A is equal to 0. All of the coefficients are equal to 1. Right? Or I guess maybe the easiest non-trivial one. Certainly I could set all the CKs to be 0, but then it's kind of boring. So there's this thing, right? And we know that this thing actually doesn't converge for all real numbers. We know that this converges if and only if what? What do we need for this to converge? Like, yeah, exactly. Right? Because this is a geometric series, right? That's what this is. This thing is a geometric series. But again, so usually in the context of how we think about geometric series, usually we kind of write this down, but we're assuming that we're going to plug an x in. Right now, we're kind of thinking of this thing as a function, say, where you're allowed to plug in different values of x. And if we think of it as a function, so if we think of this as a function, so let's say f mapping -1, 1 to r, like this. What is f of x? Does anyone remember the formula? 1/1 minus x, exactly. Right? So all of this stuff, if you're like, what the heck's going on? Where does that stuff come from? This is all just geometric series stuff, right? The formula on the left is an infinite geometric series. If you plug in any number between -1 and 1, and we know that the limit of a geometric series is 1/1 minus x, right? We've learned that before. So this is an infinite series. And for all x between -1 and 1, we converge. Now, is that convergent pointwise? I mean, certainly pointwise, right? We know it's pointwise. Is that convergence uniform? Can anyone look at this and tell me, yes, that is a uniform convergence of this series, or no, it's not uniform? Right, exactly. So this is not uniform. And the reason for that is that the partial sums are all bounded on -1, 1, right? Right, these are just polynomials, so they're certainly bounded. Are all bounded on -1, 1, right? But our function 1/1 minus x is not bounded because, it has this vertical asymptote as we approach 1 from the left. But f of x equals 1/1 minus x. Is not bounded, okay? So convergence here isn't uniform. Now, that being said, sort of the issue there is that we took the entire interval -1 to 1. If we took any smaller subinterval inside of there, right, like -0.5 to 0.5, suddenly, well, maybe it is uniform, right? Because we don't run into that unboundedness issue. And it turns out, yeah, as long as that interval isn't -1 to 1, and it's always going to be symmetric, okay? So if it was like -3/4 to 3/4 or -0.999 to +0.999, then convergence actually would be uniform in that case. In this case, it only breaks because if you actually go to the boundary, you get some sort of unboundedness. So we're actually going to prove that that basically, if you converge, what you want to do is you want to look at sort of your largest interval of convergence, and then if you shrink it down any little amount, you'll actually get uniform convergence in that interval. Okay, not in the whole thing, but within it. So there's a bunch of things we have to figure out here. And that's going to be enough to give us things like, if this thing converges, it has to be continuous. So there's a bunch of things we have to figure out. First of all, we have to figure out, what does convergence mean, right? So we have, again, this pointwise convergence, we have uniform convergence. And as we've seen in this example, we can write down these sort of infinite power series, but not be guaranteed that they converge for every real number, right? They might only converge for some subset of the real number. So we've got to figure that out. And then we've got to figure out, okay, if I define this thing to be a function, what do I know about that function? Is it continuous? Is it differentiable? Is it integrable? Yada, yada, yada. And then we're going to flip everything on its head. We might not end up doing this until next week. Then we got to flip everything on its head, and we got to say, okay, if I start with a function, is there a way of writing it like this, right? Because in this framework, in this example that we just wrote down, we kind of usually, historically, we start with the infinite geometric series and we figure out what function it's equal to. But we're going to flip that on its head and we're going to say, okay, well, if I start with a function, is there any way for me to figure out, is it equal to some sort of infinite power series, right? And that is where the study of Taylor series comes from. Okay, so we've got lots of stuff that we have to prove. And a lot of the proofs I think you're going to see are very similar, but they're all very slick. And the idea of almost every proof that we're going to do is basic comparison theorem to the geometric series, right? So if you, again, sort of look at this power series right here, it's almost a geometric series, right? If the CKs are all equal to 1, then this is basically a geometric series, just maybe sort of like shifted so that it's near A. And that's the big thing. Like that's the main proof technique. We're just going to compare everything to a geometric series. Okay, so theorem number 1 goes as follows. So theorem, given a power series, sum k equals 0 to infinity, ckx minus a to the k, there exists a unique, and it'll clearly, we're going to prove it exists, but it's clearly unique. So there exists a unique number, real number R, satisfying this. Okay, and this is a little blasphemous, right? Because I'm saying that R can be less than or equal to infinity, but there are going to be cases where we do actually want R to, I guess I shouldn't say R is a real number because this is not okay, but there is a unique number R potentially equal to infinity, which is between and potentially equal to 0 and infinity, such that if X is a number less than R, right, then the series converges absolutely. Maybe let me actually do this as a bullet point. So then 1, if X is less than R, power series converges absolutely. Pointwise. Converges absolutely pointwise. Okay, so we're not talking about uniform convergence yet. Okay, just pointwise. And if we're bigger than R, then we diverge, right? Which feels kind of like a ratio test sort of thing. You remember? And we said that you would compute this limit. If that limit was less than 1, you converged absolutely. And if it was greater than 1, you diverged. So it's very similar to that. And in fact, what we're going to see is that when we're actually computing this number, because of that relationship, the root and ratio tests are really the primary way of computing these things. Okay. And immediately, and I'll sort of write this note down, or maybe I should write this note down now, is, well, there's a missing case, right? So this tells us nothing. Oh, I guess I should write, oh, shoot, you know what? My series needs to be, sorry, because I'm still centered at A here. In the proof, I'm gonna drop the A, right? But I need that there. My apologies. X minus A like that. Okay, so this tells us nothing about what happens at R. Yeah. Okay, and the reality is that anything can happen at R. Okay, we're going to have to see a couple more examples to get that, but you can have a power series which converges at both of its endpoints. You can have a power series which diverges at both of its endpoints. You can have a power series which converges at one endpoint and not the other. Okay, so all of these things are possible. So the reality is right now this theorem tells us that this R exists, but it doesn't tell us anything about what happens actually at R And that's okay, because there's only 2 points. And the reality is you can just plug them in, right? And you can figure out what exactly your function does there. So this R is called the radius of convergence. So maybe that's 1, 2. R here is called the radius of convergence. Okay, which I might, depending if I'm feeling lazy, I might abbreviate as ROC, like that. All right, because we're going to have to write it a couple times, and I don't necessarily want to write it down every single time. But the radius of convergence, okay? And again, the idea being, like I said, we're always going to look at these sort of symmetric intervals. So we're thinking of this thing as sort of being a ball, right? And if it's a ball, this is its radius. And when you go and you do this in higher dimensions, it's literally a ball, right? Okay, so again, stare at that. What do we need to prove? This number exists. And this proof is, I think if you're staring at this for the first time, you're like, oh man, how are we going to prove that? Okay, well, the proof's not too bad, actually. So first of all, what we're going to do is set R. This is like the most cheating thing. Sigma ball? What do you mean by sigma ball? And I actually can't see whatever the emoji is there. For whatever reason, it's not showing up. Just a block for me. Oh, actually, you know what I'm going to say first? I'm going to say without loss of generality. B sub sigma. What's sigma there? Just some number? Oh, okay. Like what? Okay. Like an F sigma. I assume it's not an F sigma set. He didn't teach you about F sigma sets. And that's not what you're talking about. Because usually we use F with F sigma sets, not and G deltas. No? Okay. So I'm going to say without loss of generality, maybe that's technically not the right word, but without loss of generality, we're going to take A is equal to 0. And I will show you exactly how the proof changes if A is not equal to 0. But the answer is it changes in exactly the way you think it would, which is everywhere you see the absolute value of X, you put the absolute value of X minus A and nothing changes. Okay. So all this is going to do is prevent us from having to write the absolute value of X minus A everywhere, which is kind of a pain in the butt. So without loss of generality, let's take A to be equal to 0. And then what we're going to do, here's the R that works. And again, this feels super cheesy. But hey, we can do it. Ta-da, right? So we said R has to be this number so that this thing converges absolutely. So what are we going to set it to do? We're going to say take all the points where it converges absolutely and let R be the supremum, right? And but I mean, there's still some things we have to prove. First of all, we have to prove, that's fine. You found the supremum, but there's actually no holes in there, right? Like if R is equal to 10, there isn't a hole where if the absolute value of X is in the 5 to 6 range, then it doesn't converge. You know what I mean? So there's some stuff in there that we actually have to prove. So the first thing is, well, what happens if R is equal to 0, right? Oops. So case 1, this is when R is equal to 0. There really isn't anything to prove here, right? So if R is equal to 0, that means that the series converges only if X is equal to 0. Converges only when X equals 0. And so, yeah, it definitely diverges beyond that. And so there's nothing to do, right? I guess I can say if and only if. So there's nothing to do. Why is it called the radius of convergence? Because it really is. There is a ball, right? So remember when we were talking about topology, right? The ball of radius R centered at A is the set of points such that, X is in a minus r, a plus r, or equivalently, right, like x minus a is less than r, right? And these are the sorts of things that we're dealing with. So it is in, if our balls are sort of these one-dimensional balls, which just end up being open intervals, then that number is literally the radius, right? So that's why it's called the radius of convergence. And the convergence is that within that radius you converge, right? So that's where those two parts come from. Okay, so if r equals 0, that means that this only converges when x is equal to 0. And if it only converges when x equals 0, then it converges when x is not, diverges when x is not 0, and we're done, right? Because that's what we wanted to show. Okay, so case 2. So let's assume r does not equal 0. And so this includes the r equals infinity case, right? So this includes r equals infinity. And basically we can treat it the same way. It's just that when we prove divergence for this one, right, like we're not too worried about it because there won't be anything which is bigger than infinity. Okay, so what do we want to do here? So let's prove divergence first. So if x, the absolute value of x is bigger than r, so we want to show that it diverges, right? But of course it diverges. R is the supremum of all the convergent ones, so it must diverge. Then the sum ck x to the k must diverge. Otherwise, the absolute value of x would be, what's the words that I want to say here? It'd be in that set that I took a supremum over, and therefore r would be bigger than it, right? So this isn't possible. Yeah, but how do I, what's the word? Because I didn't define what this set was. So how do I do that without just rewriting it? Do you all see that it's true? So it must diverge. Otherwise, how do I say this? R, it can't be the supremum of the convergent things, right? Yeah, it can't be an upper bound. Let's say that. Otherwise, R is not an upper bound for the absolutely convergent points, right? So by definition, at the top of the screen, you've taken the supremum of all the absolutely convergent points. So yeah, this thing has to diverge, otherwise whatever. Okay, so if we're less than r, then we need to prove that we actually do converge. And there is something to prove here, right? And good, I'm glad that that made sense. So let's show that this thing converges. Because we actually don't have that yet, right? Look at the definition of capital R at the top. It just says I've taken the supremum. So what I have to show now is that actually I converge from any number less than this, right? Because again, there could have been gaps. There could have been gaps, and I took that supremum and find it's the biggest one, but do I know that it actually works for everything less than that as well? Well, that definition doesn't quite give it to me, right? So there's actually something we have to prove here. So this is going to be our first, chance to really see sort of how these sorts of proofs go and how we compare it to a geometric series. All right, so here's how we're going to do it. All right, so we're less than r, and we're strictly less than r. That's important. So let's fix, I almost want to give it a different name, but no, whatever. So fix sum x naught such that, oh, maybe I can call it little r. Yeah, because that's sort of more consistent with what we're going to do later. So fix some little r such that this is true. Okay, and we can do this by definition of the supremum, right? So like without going into too much detail here, hopefully you remember the epsilon definition of the supremum. So if you set epsilon, right, to be equal to r minus the absolute value of x, you'll get that this is true, right? That you can find some R between these two numbers such that you do actually converge at R. Converges absolutely. Right? Otherwise, R wouldn't be the least upper bound, right? Because you could get something smaller than it. So you have to either it is itself, like capital R is itself something which converges, or you can just choose something which is close to it. Okay, great. So we can get some point which converges. Now, let's compare to a geometric series. And the way that we're going to do this is as follows. So now, let's write CK X. Do I want? Yeah, I guess we are converging absolutely. So I have to put the absolute values around everything. So let's write this. And I'm going to do what? So I want to put RK here. And then I'm going to multiply and divide XK to RK, like so. And in fact, let me maybe take the K's out of that left-hand side. CK R to the K. X over R to the K, right? So I haven't done anything crazy, right? I multiplied and divided by R to the K. Okay, now we're in a good position. This thing here, that number is less than 1, right? Because we said the absolute, because of this thing right here, right? We said the absolute value of X is less than R. So if I take the absolute value of X divided by the absolute value of R, in fact, we don't even need the absolute value of R. We know it's positive. But if I take the absolute value of X divided by the absolute value of R, I get some number less than 1. And now when I'm looking at the terms of my series on the left, I get something which kind of looks like a geometric series on the right. The only problem is this thing right here, right? How do I deal with that? So ideally, I'd like this thing to go away, right? I'd like it to just be a constant. Because if it's constant, I literally have now my basic, like if I can say all of these things are less than 1, then I'm in a situation where I've got my left-hand side is bounded on the right by a geometric series, which converges by the basic comparison theorem. I'm done, right? So I'd like to bound this thing by 1. Why do I know I can bound this thing by 1? Not necessarily for all K, but eventually they're all bounded by the number 1. Why can I do that? Yeah, it converges absolutely. So because the series converges absolutely, what do I know about the sequence? All right, so if your series converges, what do you know about the sequence? Exactly, it goes to 0. So if I choose epsilon, I can choose what epsilon I want, right? And eventually, so I choose the epsilon and all these sequence elements must be within that epsilon, right? So in particular, if I choose epsilon to be 1, I can guarantee that CKRK is eventually as small as I want it to be, i.e. it's bounded by 1, right? So since this sum, CKRK, converges absolutely, there exists some n in n such that for all n greater than or equal to n, C little n R to the n is less than 1, right? By exactly what we all just said, right? This thing must converge to 0. So let's let epsilon be equal to 1. And now there exists some n such that this is true. So therefore, if I now substitute, and again, we have to be bigger than big N here, but if I substitute now this identity into the previous line, so thus, if N is greater than or equal to N, or let's say K, because that's what I used, we're going to get CK X to the K is less than or equal to X over R to the K. And the right-hand side, again, defines a geometric series whose ratio is less than 1. And this is a geometric series which converges. So by the BCT, CK x to the k also converges absolutely. So, right, and that's what we wanted to show. So there wasn't really a lot of math happening here, right? This proof isn't necessarily short, but most of it is like a silly case, right? When r is equal to 0, certainly converges. When r is, or when the absolute value of x is greater than r, certainly diverges. So the meat of the proof really doesn't start till about this point here, right? That's really when the meat of the proof begins. And it's basically like, hey, look, finagle this thing in such a way that you get a geometric series on the right-hand side. And again, that's going to be most of what we do. So this one I took, again, sort of slowly, just so that you could see how we're going to end up manipulating this thing into a geometric series. But this is going to be the common trick. So in the future, I'm probably just going to go straight to this line. Like I'll put that line first and then do this line. And if you see me doing that, you know why I'm doing it, right? Because I'm trying to get rid of those constants sort of thing. Sure. So it converges because, like, so this line right here. So here, let me maybe do this on the side here. Okay, so what we need is, let's come back up here to the supremum. So remember that M is equal to the sup over a set S if and only if for every epsilon greater than 0, there exists some S and S such that, okay, which way do I want? So I want M minus epsilon is less than S is less than or equal to M, right? So in this case, this is going to be my S right there. And I'm going to set epsilon to be R minus the absolute value of X. So then if I apply this, it says there's some element in this set, right? There's some number, which is the absolute value of X for some X, but there's some number, little r. Oops. So let's say set this. So there exists some number, little r, such that, so we're going to get r minus epsilon is less than r is less than equal to capital R. And if you expand out what this is, well, look at the definition of this thing. That just ends up being the absolute value of X. Okay. And again, the important sort of thing here is that this R is in S. Right? So it is something for which your series converges. By definition, that S set, is the set of things where you converge absolutely. So I've chosen something in there where I converge absolutely, and I can be guaranteed that it must be between the absolute value of X and R. Does that make sense? So when I say, yeah, this line down here, that's because we chose that little r to be one of the things in the set that I'm taking the supremum of, and I know those things converge by definition. Okay. Why are we using convergence to define S? Oh, sorry, that actually should be, oh no, we get the absolute convergence right here, in effect. Though you can say converges absolutely if you really want to. Right? Like that effectively, yeah, maybe we should add converges absolutely just to be on the safe side. Does that really get it? So let's see, let's double check here. Because I guess in theory, you could converge for X, but not the absolute value of like X converges, but not negative X converges, then you throw it into the set. Yeah, actually, hold on. Let me double check. Because either we should change this to converges absolutely, or we should do, let me just double check. So if you have some value of x less than r, let's show that this converges, fix some r such that this is true, that converges. I guess we actually don't need, that's a good point. For now, let's just change this then to converges absolutely. That is a good point, but I will double check that because what I feel is that we should be able to get it is between this absolute value and then the fact that you just choose some r in there. I'm pretty sure you can get absolute convergence, but you're right. Let's be on the safe side right now and just do converges absolutely. In the Supremum, like the definition of little r? No, in the proof. So like here? Yeah, so that is the Supremum one though, right? So again, if you look at in the definition of the Supremum, you have to put the less than or equal to on the sup itself. Oops, how did that get erased? Right, so you have to put the less than or equal to on the sup itself, because in theory, right, you could have one of those things where your set S, you know, if you were to draw it on the number line, looks something like this, and then has a big gap, right? And there's your sup. So you have to be less than or equal to in that last thing. But it's just saying like, you know, you don't know if it's going to be equal to R. Yeah, sure, right? If little r is equal to capital R, that means that you actually do converge at big R, which is great, but that's not really what the theorem is telling you, right? Because this theorem is just saying we're looking when the absolute value of x is less than big R, but it can converge at big R, right? It is possible that like, you know, little r could actually be equal to big R. That is okay. But we don't know, right? That's the point. At this stage in the proof, we don't know if something like this happens, right? Where you converge absolutely here, and then you magically converge absolutely here. Well, what happens, you know, what about this gap, right? Do we still converge absolutely in there? And what this theorem is proving is, yes, actually, this is a solid line, right? You actually converge everywhere in there. But we can't assume that, right? When we start the proof, we can't assume that something like that doesn't happen. We have to prove that that doesn't happen. Yeah. Okay. All right, so let's do maybe a non-geometric series example. Let's see what that works out to be. So example, let's say find the ROC, the rock for this series. What do I wanted to do here? 2 to the k. So here again, I'm going to start my series at 1, but of course that doesn't matter. So 2 to the k divided by k x minus 1 to the power of k like that. Okay, so that looks a little bit weird, but that's okay. That's actually not that weird, it turns out. All right. And so, like I mentioned, you know, that statement looks a lot like the root and ratio test where you converge absolutely if you're less than 1, you diverge if you're bigger than 1, and then you don't know what happens at 1. And it's the same sort of thing here with the radius of convergence. You converge absolutely if you're less than R, you diverge if you're bigger than R, and then you don't know what happens at R, right? So that's actually a big indication that maybe we should examine these things by using the root and ratio test. In this case, I'm thinking ratio test. We're close to almost being in a situation where we might want to use the root test. Maybe if that denominator was k to the power of k, we might do this. I think ratio is going to work out easier. You could do root test, but I want to do the ratio test, okay? So let's apply the ratio test. And so I'm going to take a limit. Hopefully you remember what the ratio test is, right? So I'm going to take the term of this sequence. And you're saying like, I've got a fixed x naught here, right? Maybe I should sort of say that. So you're saying like fix some x in R. And now let's just pretend that thing's not a function in x, right? We've fixed some x, so now it's just a normal series. So we can apply, that's why we can apply the ratio test at this point. So I'm going to take that term, but at +1, right? Times the absolute value. So again, implicitly, I've sort of taken the absolute value of everything, but almost everything here is positive anyway. This is the only thing I really have to worry about. And then you divide. So this is the k+1 term. I'm going to divide by the k term. So if I do that, I'm going to get, what, 2. I'm going to get k divided by 2 to the k, x minus 1 to the k. We get a ton of cancellation. So what's going to survive? So we're going to get the limit as k goes to infinity. So we're going to get 2k over k plus 1 times x minus 1. Right? And again, the absolute value of x minus 1 here is a constant. And I mean, so is the 2. So we can really pull those out if you want. Maybe do that just for the sake of demonstration. At this point, you can write down the limit if you want, but let me just pull those out. Just to, again, sort of emphasize they are actually constant in this expression. Now I've got this thing, k over k plus 1. That's just equal to 1, right? Using our usual trick, multiply and divide by 1 over k. So we get this, right? And that's good. And so now what we say is, well, again, by the ratio test, this will converge absolutely if x is 2 times x, the absolute value of x minus 1 is less than 1, right? So by the ratio test, the series converges absolutely if 2 times x minus 1 is less than 1, and diverges if 2 times x minus 1 is bigger than 1. And so we can use this now to find what the radius of convergence is by solving for the absolute value of x minus 1. So the radius of convergence is 1/2. And we're done. All right. So here we're really leveraging that the root test precisely matches the statement of the previous theorem, right? We know there's a number such that if you're less than that number, you converge absolutely. If you're bigger than that number, you diverge. Well, the ratio test just happens to tell us the exact same thing. So if I take, if I use the ratio test to compute something on just a generic x, and I get 2 times the absolute value of x minus 1, I'm going to say, what sort of condition then do I need for the root test, the ratio test to tell me this converges absolutely? What do I need for it to tell me it diverges? Oh, the number 1/2 works. And so if I'm less than 1/2, I converge absolutely. If I'm bigger than 1/2, I diverge. That has to be the radius of convergence, right? It's the only thing that it could be. And so that's how we get it. And so again, hopefully you see that the root and ratio tests are exactly the things that you want to apply in order to be able to find radii of convergence. Because just finding where you converge or just finding where you converge absolutely isn't enough to find the radius of convergence. You also need to know where you diverge, right? But the root and ratio tests give you exactly that. And so that's phenomenal, right? That's exactly what you want in that. So you can use that to figure this out very, very quickly. And that's why I say root and ratio tests are the sorts of things that we're going to use the most. And not only that, if you think about what both the root and ratio test, when you apply them to a power series, are always going to give you your absolute value of x minus a term out, right? If you think about it and you look at it, you're always going to get the absolute value of x minus a just sitting there, right? It's just going to plop out. And that's what you want to happen, right? That's exactly the thing that you want to happen. So yeah, these are the tests that we're going to use. Okay, any questions about that? And you see it's actually not too hard, right? It's not too hard to compute radii of convergence in general. Okay, so let me say something else very quickly here. So again, our theorem above doesn't tell us anything about what actually happens at the endpoints, right? It doesn't tell us what happens when we're equal to our radius of convergence. And anything can happen. So sort of again, maybe let's write this as a note. So the domain of convergence includes the endpoints if your power series converges there. If the power series converges. Okay, so the radius of convergence is always always ends up giving you this open interval, but you might want to cap it off, right? So you have to just check those by hand, since there's only two endpoints. There are only two endpoints. Just check them by hand. Okay, and again, for the record, every possibility can happen. Okay, you can get convergence at both endpoints, divergence at both endpoints, and convergence at the left endpoint, not at the right endpoint, and vice versa. So the geometric series that we've seen before does not converge at either of its endpoints, right? Let me scroll back up, and I'll come back to that. So we've got our geometric series here, and we said its radius of convergence is 1, right? Because we know it actually diverges if we're bigger than 1. So what happens if x is equal to, if x is equal to 1, right? Or -1. Well, if x is equal to 1, your series definitely doesn't converge, right? Because you're just adding 1 to itself over and over again. So it doesn't converge. When x is equal to -1, you don't get convergence either, right? Because you get -1 plus 1, -1 plus 1, -1 plus 1, -1 plus 1. And so your partial sums become 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. And that doesn't converge to anything, right? So geometric series doesn't converge at either endpoint. However, you can imagine the reason I gave you this one is it's going to exhibit a different behavior, right? So let's find out, and then we'll go on break. So example, find the domain of convergence for, and again, I'm just writing out the same one I wrote above. So 2 to the k over k, x minus 1 to the k. Okay, and like I said, in this case, you just have two endpoints, right? We said the radius of convergence is 1/2. So let's just plug in what happens when r is equal to 1/2, right? And that corresponds to the absolute value of x minus 1 being equal to plus or minus 1/2. Okay, so solution. Let's check what happens at x minus 1 is equal to 1/2, right? And again, like if you really wanted to solve this, you could, right? So this means what, x equals 1/2 and 3/2. But what you'll notice is that when you plug that into here, right? If you plug 1/2 into there, you get -1/2. If you plug 3/2 into there, you get a +1/2. So that's really just the same thing as taking plus or minus this and replacing it into the x minus 1 term, right? Just save yourself a little bit of time. Think through why that's true, okay? So instead of solving for what the actual x's are, you can just take x minus 1 to the k and replace it with plus or minus your radius of convergence. So on the one hand, all right, so let's maybe do the left endpoint first. So k equals 1 to infinity. So we get 2 to the k all over k times -1/2 to the k like that. right? So that's what happened if I plug in x is equal to a half. I get 1/2 minus 1 to the k. So that's a negative 1/2 to the k. And look at what happens. Right? Converge or diverge? Converges by the alternating series test, or that it's basically the alternating harmonic series, right? Which we know converges, but alternating series test is what you would use. For the right-hand side, so we get the sum from k equals 1 to infinity, 2 to the k over k times 1/2 to the k. Oops, 1. And we know that feller quite well, right? That's the harmonic series diverges, right? So in this case, domain of convergence is 1/2, 3/2 open. Okay. And it's not too hard to find series where you actually converge at both endpoints. So mess around with it, see if you can find one. Generally, you want your, well, I guess that's actually not strictly speaking true. I mean, just throw a random sequence in front of a power series and see what happens. You know what I mean? In fact, one thing, and we were kind of talking about this in office hours yesterday, one thing you might want to do at this point is just even take this power series, if you're just trying to get a better feel for, you know, how these things sort of work, take this power series and mess around with it, right? Change the 2 to the k to a 7 to the k. How does that change your radius of convergence, right? Change the x minus 1 to an x plus 3 or something like that. How does that change your radius of convergence? Change the k in the denominator to k factorial. Change it to k to the k. Change it to k squared, right? You don't have to invent a brand new series. You can take the series that I've already given you and just mess around with it a little bit and see how it's going to affect the radius of convergence. Does changing it to k squared make any difference, right? Like, is there any power of the denominator that is going to change? Does changing 2 to the k to the 3 to the k make a difference? It does. But does it change like whether the left endpoint converges to the right endpoint? It doesn't. Like, what's going on there, right? And you'll start to get a feel for sort of like how this example works and how it's structured. But if you change the denominator to k factorial, suddenly things are different, right? So mess around with that for a little bit on the break if you want. And then what we're going to do is, I think, let me just kind of give you a preview of what the next thing is. Right. So we're going to prove uniform convergence. So we're going to prove, basically, we know that we can't, whatever this thing is doing as a function, it's not converging uniformly on its radius of convergence. But what we want to show is that if you take literally any smaller symmetric interval, right? And so instead of taking a minus big R to a plus big R, take a minus little r to a plus little r for any, you know, little r that's smaller than big R, then you do get uniform convergence. And if you want to try and prove that, the proof is almost identical to the existence of the radius of convergence, okay? It's very, very similar. So that's sort of like a good little thing you can do on the break as well if you want to give yourself a shot. So it's 10:07 by my watch. We'll come back at 10:17. Let's take a 10-minute break. And then I'll prove uniform convergence for you, and then we'll start differentiating and integrating these things. Okay? And again, as always, you know, throughout, ooh, that's weird. Uh-oh. It's not supposed to look like that, right? Anyway, we'll prove uniform stuff when we get back. What are you doing? Zoom. Oh, that's not Zoom. That's OneNote. Notes. Don't be deleted. Whew. Okay. Everything's all right. Nobody panic. Yeah, it has been. Yeah, I guess I maybe just sort of mentioned it in class, which you might not have seen. I do have to formally still actually submit the syllabus change. But yeah, it will be take home. I'll probably post some information about the final this week, actually. Oh, so now you don't see OneNote? That's very weird. Why don't you see OneNote anymore, Zoom? There it is. Yeah, let's zoom out a bit so you can see some stuff. And then okay, everyone, we're back. All right. So what did I say we were doing? Uniform? We're going to do uniform. Too much zoom. All right. So let's prove uniform convergence. I said it's pretty much the exact same because it is, but there is an important difference. And we'll see. I'll sort of point out what it is as well. Okay. So maybe I should just make as a, wait, did I already say as a note? I did. I did say it was already like not, like we knew that the convergence couldn't be uniform in general, right? So our theorem here is if the sum, do I want to state this as a function? No, I don't want, yeah, I guess I do. So if sum ck x minus a to the k equals 0 to infinity is a power series, let f mapping a to r, a plus r to reals given by this 0 to infinity ck x minus a to the k be its corresponding function. Where r is its radius of convergence. Oh man, this is so wordy. Yeah, that's just the way theorems are sometimes, right? Okay, then for any little r between 0 and big R, so for any little r in R such that 0 is less than or equal to r is less than r, this series converges uniformly. To f. Okay, so we can't, or I guess to f on, I should finish that sentence, a minus r, a plus r, right? So basically, yeah, you can't do it on the whole interval, but yeah, shrink down to any, like literally any smaller subinterval and you'll get uniform convergence. Okay, so it's really just those endpoints that sort of give you an issue here. So we'll get uniform convergence if you shrink. That's all this theorem is saying, right? It's fairly wordy, but it is what it is. All right, so proof. All right, so let's start by fixing that little r. So fix 0 less than equal to r less than r, right? All right, now what do I want to do? And take some. All right, so this is kind of backwards from last time, but whatever. Right, and we can do this. Right, and we're not even guaranteeing anything. We're just saying literally just choose some number, some point x naught, such that the absolute value of x naught is between r and little r. Okay, and of course we can do that. That's just completeness of the real numbers, right? Okay, so we know, I guess, do I need the absolute value here? I guess probably, well, yeah, no, I do. So we know, I forgot to say take a to be equal to 0. Every single proof is A is equal to 0. Okay. Just in case I forget to say it at the beginning, every proof A is equal to 0. Otherwise, here, just put x naught minus A less. The absolute value of x naught minus A is less than R, right? So we know that the sum of ck x to the k then converges absolutely. Or sorry, x naught. Right? Because the absolute value of x naught is less than R. So we know it converges absolutely pointwise. So let, again, capital N in N be such that ck x naught to the k is less than 1 for all k greater than or equal to n. Okay, so that's our usual trick. We know that that series converges, absolutely. So in particular, you know, its sequence has to go to 0. So just go far enough in that it's less than 1. Okay. All right, and then what do we get? So now here's sort of the important step. So we're going to do our usual sort of bounding little trick here. So now, thus for any x in negative R to R, we have, so there's a lot of numbers kind of flying around here, right? All right, so do I want to replace this with x or x naught? Okay, I want to replace it with x naught. So we're going to do x naught to the k times x. I wonder if could I have gone straight to, could I have gone straight to R? I don't think so. Yeah, because I need this to be less than 1 here. So like that. Okay, that's not good enough, right? So fine. This is still less than 1, right? Because we know that the absolute value of x here is less than R, which is less than the absolute value of x naught, which is less than big R, right? So that's what I'm saying, right? There's a lot of sort of inequalities here. So this number here, this is less than 1. This is a geometric series less than 1, but this isn't good enough. This does not give me uniform convergence. This is the sort of thing that, hey, if I'm doing pointwise convergence, great. By the basic comparison theorem, this thing converges, but I need uniform convergence, right? So what do I do here? Does anyone see? What theorem did we talk about on Thursday that gives me the result that I need? Right, exactly. Yeah, the M test. So what do we know? So we know that x naught is bigger than R, so I can now replace this by x over R. No, is that what I want? No, I want R over x naught. Like this. Right? This is now, this does not depend on x, right? So what we've done here is we've said, we're looking at the individual components of this infinite series, right? And now I've bounded each of these by this number m sub k. And the m sub k's, though, do converge, right? Right, so we've bounded ck x to the k by the constant, right? For a fixed k, this is a constant, R over x naught to the k for all x in negative R, R. Okay. Moreover, those things on the right, the series of the MK's convergence. Moreover, R over x naught to the k is a geometric series. Is a convergent geometric series. Right? So by the Weierstrass M test, that means, therefore, that our thing actually converges uniformly. is a convergent geometric series. So by the M test, converges uniformly. And we're done. Okay. Now, again, what you want to do is once you've proven something like this, you want to say, well, why couldn't this have worked, right? If we had taken the whole interval. And this is sort of the important step right here. Right? So there's a ton of numbers involved here, right? And you can kind of see those again in this like little chain that we set up here. But you see, like, there's no way I could have set up these numbers if I was looking at the entire interval big R, right? I really needed to be able to sort of do this straddling in order to make this, bounding argument happen. And that doesn't work if I can't find some X naught between these numbers, right? Between little r and big R. So if I tried to do this and I set, little r to be equal to big R, suddenly I can't find X naught. And if I can't find X naught, well, now I'm in trouble, right? Like, how am I possibly gonna do this? I just can't, right? If you sort of do the same sort of result here, but you replace little r with big R, this number is sort of like, suddenly becomes 1. So all of your MKs are now the number 1, and that thing's not going to converge. So we've needed, right, in order, at least for this proof, in order to work, and again, we know it's not going to work in general, but if we look at this and say, well, why does this proof work? It's precisely because, taking a number slightly less than our radius of convergence gave us a little bit of wiggle room so that I actually could do some sort of bounding arguments, right? Which I couldn't do if I was actually at the limit of my radius of convergence. Okay, make sense? Okay, so immediate corollary, though, it turns out, like, you might say, well, that kind of sucks. It'd be nice if we had uniform convergence on the entire interval. And I agree, it would be nice, but it turns out we don't really need it. So if we define this function, x minus a to the k, where r is the radius of convergence, then f is continuous. Okay, so same setup as before. You give me some sort of power series. We look at the function on its open interval, right? And we say, hey, look, turns out actually the function is continuous on that entire interval. And again, maybe that shouldn't be surprising, because if you look at the power series, where is something going to go wrong, right? Like, you're constantly just adding on these continuous functions, right? In fact, these like differentiable functions. So you just keep on adding on these differentiable functions. Everything's behaving exactly how you want. Like, these are big old polynomials. They're the nicest things you can deal with. And so we're saying, actually, you're continuous on your entire interval, not just any subinterval. You're continuous on your entire interval. And the proof of that, there's almost nothing to do, right? Because by uniform convergence, we the partial sums here are continuous. So the partial sums I guess in this case, we don't have to set a to be 0 because we're not going to say much. But in this case, the partial sums are clearly continuous. Oop, that should be n. Right? They're just polynomials. And because they converge absolutely, that means that their limit must also be continuous, right? On a minus little r to a plus big R for any r. Their uniform limit f is continuous on a minus r, a plus r for all r like that, right? But that actually gives you continuity everywhere. Because if you want to say, hey, listen, am I continuous at, this point, which you do, this point, which is not equal to big R, what do? You just set little r to be a little bit further than that, right? That's the benefit of working with open intervals. So yeah, so it's continuous on this. So thus, if x naught is in a minus big R, a plus big R, right? Choose little r so that x is in a minus little r, a plus r, and now f is continuous at x. Right? So you can literally do this for any point precisely because this is an open interval, so you can't choose its endpoints. So if you give me any point in this interval, I can find a little r that encapsulates it and therefore has actually uniform convergence, and therefore my limit is continuous on the entire interval. So restricting our uniform continuity to a subinterval, not that pricey, right? We're still able to make it work out. If you look at those examples like of x to the power of n, right? In that example, you'll notice that this trick doesn't work. And it doesn't work precisely because when we were doing when we did this example, this didn't work because we were using a closed interval here, right? Otherwise, we totally could. Like if you're doing sort of a uniform limit on an open interval, and if you can guarantee uniform convergence on any subinterval, then you'll get continuity in the entire thing. Here, this broke though. We weren't able to do something along those lines precisely because we had this closed interval, and the discontinuity point happened at one of the endpoints, right? Like that was really the problem, okay? Because the x to the n's, for the most part, were trying to converge to zero. That's what they wanted to do. They wanted to converge to zero. And the problem that was really giving us trouble was at the point x equals 1. So, we run into a little bit of troubles when we're working on that sort of closed interval there, but we've got that open interval, we can do a lot more. Okay, so boom, we've got continuity. Now we can't get boundedness from this, right? We know we can't get boundedness because the problem is that sure, we'll be bounded on a minus little r to a plus big R, right? That's true. But as I let r get, little r get bigger, or as I change little r, I'm going to get different bounds. And in general, those bounds could themselves be getting bigger, right? And again, we sort of know that from our geometric series example, which is unbounded near x is equal to 1. And again, we see that why this is true. Yeah, it's bounded on any subinterval, but as you let little r get bigger, those bounds become bigger themselves. So we can't sort of apply the same technique for boundedness as we did for continuity. All right, so hopefully that makes sense. And then there's the big one. I hope I can finish this proof today. I don't know, we'll find out. Okay, so we do get continuity, but there's a more important thing that we get as well. So if the sum from k equals 0, be careful with the indices for this question. X minus a to the k has radius of convergence big R. Okay, notice this sum is starting from 1. It doesn't really matter. Also have radius of convergence R. okay? And again, on your first glance, you might look at these, you'd be like, okay, well, why do I care about these? And hopefully you recognize that if we were to treat the right-hand side as a polynomial, these are precisely the differentiated and integrated series that we would get out, right? So if we were to differentiate the left-hand side, or sorry, rather, if we were to differentiate the power series, we would get the left thing, right? We would get this thing. And if we integrated the right-hand side, say from a to x, then we would get the right-hand side, right? We would get this thing. So these are the differentiated and integrated power series. And what we're going to show is that, yeah, your function is actually differentiable and it's integrable. So, if you have a function defined in terms of a power series, it is both differentiable and it is integrable. And, its power series representation will be given by these two series, right? So that's sort of like what we're building up to. But the first thing that we have to do is we have to prove that it still has a non-trivial radius of convergence. But more importantly, it has the same radius of convergence of the original function, right? And maybe that's a little bit surprising. Perhaps even more surprising, if you believe this theorem, the radius of convergence doesn't change. The more surprising thing is the domain of convergence can change, though. Okay, so it is possible for you to, one of these functions to say converge at both endpoints, but then its differentiated power series, even though it has the same radius of convergence, suddenly doesn't converge at one of those endpoints. Okay, that can and will happen as a general rule. Okay, so we want to show that they have the same radius of convergence. All right, this proof is pretty long. So hopefully we'll get most of it done today. So basically what we're going to do is we're going to prove that the differentiated power series has the same radius of convergence, and then we're done, because the integrated power series, if we differentiate it, we get the original thing, and therefore they must have the same radius of convergence, right? So it suffices to show, well, okay, let me again just say, take a to be equal to 0 before I forget. So it suffices to show that ck(x to the k) and ck(x to the k minus 1) have the same radius of convergence. Because then what you do is you just apply like that theorem to the integrated power series, and it tells you that it must have the same radius convergence as your original function, and you're done, right? Or then we apply the theorem to ck(k plus 1), x minus a to the k plus 1, and ck(x to the k). Right, which again will say they must have the same radius of convergence. Okay, so let's start off with what happens if we take a radius of convergence equal to 0. So case r is equal to 0. So we're going to start by assuming, again, that the original series converges if and only if x is equal to 0. So assume, right, that's what r equals 0 means, right? So assume that the sum of ck(x to the k) converges if and only if x equals 0. Okay, now clearly again, every power series, it is also k minus 1 in the theorem. Oh yeah, you're right, k minus 1. Why did I hit k plus 1? K minus 1, thank you. So every power series converges at its center, right? Like you don't have to do anything because it's just always 0. So certainly the differentiated power series is going to converge at 0 in this case as well. So the more interesting thing is we have to show that it diverges when x is not equal to 0, right? That the radius of convergence can't grow when you differentiate the power series. So suppose, let's say clearly the sum of k ck x to the k minus 1 converges at 0. So suppose x naught is not 0, right? We need to show divergence. Now for divergence, this is a relatively straightforward basic comparison test. So we're going to get, well, let's just say x. X is not equal to 0. So we're going to get c, so k, c, k, x to the k minus 1. Okay, now that's going to be greater than or equal to ck x to the k minus 1, right? Because the sum, first of all, the sum starts at 1, but even if it didn't, it doesn't matter. K is bigger than or equal to 1. Right? So we can just get rid of the k and put a greater than or equal to sign. And again, we're okay using greater than or equal to because we're trying to prove divergence, right? So we just get rid of the k. And now what I need is to get ck x to the k, but I have ck x to the k minus 1. So let's add and subtract an x. Right? And again, I can do this because we just said x is not equal to 0. Like this, right? And this is, again, we're not talking about anything uniform. So this is, 1 over the absolute value of x. That's a fixed number for any choice of x. And we've already fixed x not equal to 0. And this thing diverges by assumption, right? So by the BCT, the sum of k, ck, x to the k minus 1 is going to diverge as well. All right. Now, the rest of this proof is much harder. So here's the case where r is not equal to 0. And of course, again, this also includes the case where r is equal to infinity. Okay. So what we want to show is we want to show that the radius of convergence for the differentiated power series is the exact same, right? So we want to show that if we're less than r, then we converge, absolutely. And if we're greater than r, then we diverge. So suppose that we're less than r, and let's show that k, ck, x to the k minus 1 converges absolutely. All right. What do I want to do here? I don't need that. Okay, so fix some little r in r such that the absolute value of x is less than r is less than big R, like so. Okay, and now we're going to, again, we want to get some sort of basic comparison tests going on, right? Because we know that the original series converges at this x by definition of what big R is. So we need to do some sort of manipulation, right? So we're going to get the absolute value of k, ck, x to the k minus 1. Now I can't use that greater than or equal to trick from before. It's not going to work. But I do now have this bigger number r, which again, I do have convergence for. So maybe we can use that in some way, right? All right, so this is going to be equal to what? So k is already positive, so I don't need to worry about the absolute value. So this is going to be k. What do I want here again? Right. So x over r to the, do I want k or k minus 1? Okay, my notes say k minus 1 times 1 over r times ck r to the k like that. Okay. There's a whole bunch of stuff there. Let's just double check that it actually does work out. Okay, so the k at the beginning here, yeah, that's just coming along for a ride. Who cares about that? I have x to the k minus 1, right? I have r to the k. And then I do have, 1 over r to the k minus 1, and then another 1 over r. So those all cancel each other out, right? So these two things are in fact equal. The things that I've taken outside of absolute value signs are already positive. So there's no issues there. So yes, in fact, the r to the k's all cancel each other out. And this does work out. Okay. So what I want to do now is sort of a similar thing. What I want to do is I want to say, let's find some way to bound this. Okay, I want to make this thing less than 1. Just like, kind of before when we said find some big N such that ck x to the k is less than 1, we want to do the same thing with this. Now, the problem is that we don't actually know whether or not this thing, goes to 0. So we need to show that this thing goes to 0. That's going to be surprisingly tricky to do directly. So what we're going to do is we're going to show that the infinite series with this thing converges, and that will tell us that the series goes to 0, or the sequence goes to 0, which seems like a weird way of doing things, but whatever works. So we claim, maybe let's give this equation a name, because I think we're going to have to come back to it. So we claim that the limit as k goes to infinity, k x over r to the k minus 1 is equal to 0. Okay, and again, that's sort of like, hopefully that's clear. Just from an intuitive viewpoint, this, x over r is less than 1, and as I take higher and higher exponents of that thing is probably going to dominate as k goes to infinity. On the other hand, though, it is being sort of tempered out by this number in front, k, which is itself getting bigger. So it's not quite clear, but exponentiation usually beats linear stuff. So we just have to be a little bit careful about that. So indeed, let's show that the sum from k equals 1 to infinity of k x over r to the k minus 1 converges, right? Because that will give us what we want. All right, by the ratio test, so we're going to get k, or rather the limit as k goes to infinity of k x over r to the, or I guess this should be k plus 1, right? To the k divided by k x over r to the k minus 1. So this is going to be, I'm just going to get an x over r out times the limit as k goes to infinity, k plus 1 over k. Again, that's just equal to 1. So I get absolute value of x over r, and that is less than 1, right? So again, this is this sort of like justification that the exponential will win out in the limit. And so by the ratio test, this thing does converge, right? Okay. So knowing now that this sequence goes to 0, we can do our usual trick where we say, well, eventually it's going to be less than 1. So let n be a big positive integer such that for all k bigger than or equal to n, kx over r to the k minus 1 is less than 1, right? And plugging this into star. Gives, okay, so what do we get? So we're going to get k ck x to the k minus 1, which was equal to k x over r. So I'm just kind of repeating that line there. Ck r to the k is less than ck rk, right? If k is greater than or equal to n. This thing converges. So by the basic comparison test, the left-hand side converges as well. So by the BCT, k ck x to the k minus 1 converges absolutely if we're less than R. Okay. That's only half of it because this doesn't tell it, right? All this tells us is that the radius of convergence for the differentiated power series is at least as big as little r, right? It could be bigger. So just because it converges for all, absolute value of x is less than r doesn't mean it can't converge for more things, right? So we also have to prove that it diverges if we're bigger than little r, or sorry, if we're bigger than big R, right? Because that will tell us that it's actually the radius of convergence. But in theory, right now, we don't know that. It could converge for actually more things. So the radius of convergence could get bigger. So now we have to show it diverges if we're bigger than R. So now we show that if the absolute value of x is bigger than R, luckily this proof is a little bit quicker. K C K x to the k minus 1 diverges. Right? And if we do that, we're done because then they do really have the same radius of convergence, right? Capital R is the radius of convergence of the original power series, and the differentiated power series also satisfies the same, converges absolutely if you're less than it, diverges if you're bigger than it. So it would be the radius of convergence. Okay. This proof, is significantly more straightforward because we basically are just going to emulate the proof that we did for the R equals 0 case. Okay. So what do we want to do here? Let me just double check, blah, 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 blah. Right, okay. So we've got this to be true. So we know the original power series diverges. So now I've got k ck x to the k minus 1 here. Again, greater than or equal to just ck x to the k minus 1, right? Because again, we're doing divergence. So greater than or equal to is sort of exactly what we want. And once again, we can just do this thing. Ck x to the k like this, right? We know x is not 0 because it is bigger than R, right? Bigger than big R. And this thing diverges here. Right? So now by basic comparison theorem, this also must diverge. So by BCT, the sum k ck x to the k minus 1 diverges. Thus, the sum k ck x to the k minus 1 also has ROC equal to R. And we're done. Okay, so there's some work there. That's not a straightforward proof at all, right? It again, sort of like differentiation is all we really want to check. Integration is usually much better behaved anyway, but in this case, there's just sort of this ladder, right? And if you can prove that if you step down the ladder, you preserve your radius of convergence, then when you step up a ladder, it must also be true because you say, well, let's go one rung up the ladder. That has some radius of convergence. If I step down the ladder, which happens to be my original power series, that must have the same radius convergence as the one above, right? And so every rung of this ladder must have the same radius of convergence. It doesn't matter how many times you differentiate, how many times you integrate, that radius of convergence is never allowed to change, right? Which is, again, sort of like a surprising thing. No matter how many times you do this, your radius of convergence can't change. But what it really speaks to is the importance of the coefficients, right? How important ck is to your radius of convergence, like really even more so than this k or k squared or whatever term that keeps popping in because you keep differentiating, or 1 over k squared because you keep integrating, right? So the radius of convergence is really more dependent on the ck's than it is in terms of any polynomial in k itself. Okay, so that's that kind of takes care of that. But note, we still have to be really, really careful about something, right? Because we know that uniform convergence does not preserve differentiability. Now we're going to get lucky. Power series are really nice. They're not just sort of your standard thing that you're taking a uniform convergence of, right? Like they're polynomials. In some sense, they're like really, really nice. Some of the nicest things we can ask for. So what we want to show is, okay, if, right, I want you to think about what we have to prove now, because this might be a little bit subtle. So if f is the function that, is equal to the power series on its radius of convergence. We want to show that function is in fact differentiable, and that what you think, and that this is the power series of its derivative, right? Because we haven't actually shown that that's true. Even if you have uniform convergence, we know uniform convergence is still not enough for differentiability. But with power series, things are nice enough that we will actually be able to do this. So we want to prove that our function is differentiable, and that is its power series. Then we want to prove that if our function is integrable, which we get for free because we know that uniform convergence preserves integrability. So we want to prove that that our function is integrable, and that this is the integrated power series, right? So we have to actually prove those things. Like that's not immediate. There's a little bit of work that has to be done there. Okay, so that's what we're going to do next time. And like I said, you can kind of get started on those. Those proofs aren't terribly hard. And in particular, the theorem that we talked about, remember when we were talking about, we said there was a theorem for differentiability of uniform convergence. We have that, okay? That is exactly what we have set up, right? We needed that the original sequence of functions were differentiable and they converged to something, and then the derivatives converged to something as well. And if the derivatives also converged uniformly, then we in fact had that their derivatives were equal. Well, this thing has the same radius of convergence, so it converges uniformly on any subinterval, right? And it's differentiable, certainly, because it's just, or rather the partial sums are differentiable because they're just polynomials. So we have exactly the theorem we need, and that proof ends up being like 2 or 3 lines. Okay, so that's, I guess, what we'll do next time. There's a lot that we did, a lot of proofs today. Could be a little bit overwhelming, but just take some time and think about it, and hopefully it'll start to make sense. Okay. Did we miss a 1 over r where we plug into the star equation? Let's see. Oh, you're right. There is a 1 over r, but that 1 over r doesn't actually affect anything here. So let me put the r there to cheat. And again, r is constant. So yeah, you're absolutely correct. I did miss a 1 over r. Luckily, it doesn't affect anything, right? Because it is a constant that we sort of fixed ahead of time. And so we still get this convergence. Like it's not changing with k, right? But you're right, good catch. Okay, everyone. So that's going to take care of it. I will see you all bright and early on Thursday. And then you have a test on Friday. Well, I guess you have a test that night, like Thursday night, but whatever. You have a test on Friday. So I'll see you then. No problem. Thanks, everyone. Yeah. All right. I'm going to close the meeting now. Goodbye, everyone. Thank you for coming, and I'll see you on Thursday.